All right, class, welcome back. This presentation is going to be on really the kinetic molecular theory and how it explains the liquid state and the gaseous state, or excuse me, the solid state. So we'll start with liquids. We already talked extensively about gases, but liquids, okay, are kind of the in-between state. Liquids are the state of matter with a definite volume and an indefinite shape. You can write down that liquids take the shape of their container, okay, but they maintain their volume. So if, as I sit here, there's a cup of tea next to in my study here, and it's in a certain fixed volume in a glass teacup, if I were to spill it on the floor, it'd still have the same volume, but definitely a different shape. So that's what we mean by that. And if you remember, in terms of the kinetic molecular theory, okay, remember the two keys of the kinetic molecular theory is just to think in terms of the speed of the molecules, okay, the energy the molecules have, and then, of course, the attraction between those molecules. So the kinetic molecular theory is going to boil down, no pun intended, okay, to both attraction and speed. Okay, so the kinetic part of it is the speed, the molecular part of it is the attraction, and that's what you're going to see out of this theory. So liquid states are between, obviously, the gas and the solids. Okay, unlike the solids, the liquids are not as rigidly held, the molecules in a liquid are not as rigidly held in place. They are able to move, so therefore they have a higher kinetic energy or movement. But unlike a gas, they have much lower, or much higher, force of attraction between the molecules. And these liquids and gases, but obviously liquid is a fluid. It's the molecules are able to flow past one another. So liquids are similar to solids in some ways and similar to gases in some ways. And when it comes to gases, they're similar in the sense of flow. There's a lot of kinetic energy in the molecules, therefore they are able to flow past each other, but they're not as free to move as a gas because there are some strong forces of attraction keeping those molecules together and attracted to one another. Okay, so if you remember my dance move, these things, the molecules kind of flow on each other, and that's the best picture of this state. And again, liquids and gases exhibit the ability to flow and therefore are both fluids, but fluid is really a substance that can flow and therefore take the shape of its container. So obviously by that definition, that would include both liquids and gases. So let's talk about some of the properties of liquids. Okay, liquids have relatively high density. Okay, they are compressible. It's a lot harder to compress a liquid than it is a gas, but they do exhibit some compressibility. For the most part, though, they're very difficult to compress liquids. Why? Their density is high. Remember, density, okay, is a function of the mass divided by the volume, okay? And if your mass is very large and your volume is very small, in other words, a large numerator divided by a small denominator, you're going to get a large density. However, if your mass is very small and your volume is very large, and you're going to get the opposite, you're going to get a low density. So when we talked about gases, the mass of the molecules are so small they're almost negligible, and the volume between them is so great it becomes a huge issue. Density of gases is very, very small, so they exhibit the highest sense of compressibility. We talked in class about compressing nitrogen gas, actually liquefying it when we lower the temperature enough and increase the pressure enough. So we can actually liquefy gases through compressibility. But for liquids, they're very, very low compressibility, though they do exhibit compressibility, if that makes sense. The density, therefore, in liquids is very high. Not as high as in solids, but definitely much higher than in gases. Diffusion, if you look at the picture down here of the green food coloring being placed in water, obviously given enough time, initially you see the green colorful food coloring goes in, and it's concentrated in the left side. This picture here shows it very concentrated right here, and then over time that green is going to be evenly diffused. So the middle one here shows that diffusion process. The reason why this happens is because those water molecules have energy. They're always moving. We look at a glass of water and we think nothing's moving. In fact, all those molecules are moving. In fact, some of them are moving at a quicker rate than others. And we talked about temperature being a measure of the average kinetic energy of the sample. So not all water molecules are created the same. Some of them are moving quite quickly, some of them not so quickly. I just sneezed, excuse me. But eventually, because of the kinetic movement of all water molecules, you're going to get to a state that looks like this, where your green is going to be evenly distributed. Okay, that is a testament to the fact that even though we don't think water molecules are moving, indeed they are. Okay, so just wanted to show you that. That's a picture of diffusion as well. Okay, now water really, the best example of a liquid that exhibits some of the properties we're going to talk about now is water. And one of those is surface tension. So a lot of these properties really can be summed up best by studying water. Water is a great study on this stuff because though it's a liquid and there's flow, you also have hydrogen bonding in water. And hydrogen bonding in water is really the polar shape of the water molecule. We talked about that. You know, this shape, it's not a linear molecule, but it's bent. We talked about VSEPR theory. We looked at that, and I told you that this angle here is 104.5 degrees, very unique to water. Okay, this bent shape is due to an unequal sharing of the electrons between the highly electronegative oxygen end of the molecule and the slightly positive end and the hydrogen end of the molecule. This gives rise to what we talked about at length in class, this concept of hydrogen bonding. It's due to hydrogen bonding gives rise a shape, the polar shape in the whole hydrogen bonding. And the hydrogen bonding, as expressed in water, give rise to a lot of unique characteristics. One of them being surface tension. Okay, if you've ever saw a Jesus bug on a lake, the ability of a bug to walk on water, I like to call them Jesus bugs. The reason why they can do that is water exhibits a high surface tension. Okay, in other words, at the surface, the water molecules bind to themselves very strongly. And it causes a tension that is because of hydrogen bonding. You see that, and you know it's unique. If I drew a test tube, okay, what you see at a water, this is called a meniscus. The edge here, water does something that looks like that. So let's just pretend this is water. It's a terrible drawing, but this is our test tube with water in it. The meniscus forms. Okay, now it's interesting because here you see it dip down. Okay, that's the cohesive forces of water. They bind to themselves. That's that surface tension. But notice here it kind of goes up the side of the test tube. That's called adhesive forces of water. Not only do water molecules stick well to themselves, exhibiting high surface tension, but they also tend to adhere to the glass molecules that wall this test tube. For comparison purposes, if I were to show you a test tube filled with mercury, mercury's meniscus looks like that. Very interesting. Quite the opposite. Mercury shows strong cohesive properties. They bind to each other strongly, but very low adhesive properties. They won't climb up the side wall of this thing because of the low adhesive properties. So that's the difference between the menisci of water on the left and mercury on the right. But water exhibits its unique meniscus, okay, largely due to the surface tension. It has attractive properties not only to itself, but to the walls of the container. That surface tension, okay, the surface of a water, due to hydrogen bonding and the unique polar shape of water, has a greater tension. So Jesus bugs and things like that exist. It also gives rise to something called a capillary action. I don't know if you remember what this is from science class, biology, maybe last year. But what happens in the tree root, ever wonder how water goes all the way up like a redwood in California? Goes all the way from, on the bottom, on the ground to, several hundred feet in the air. What happens is that the tree is filled with these vessels, much like our arteries and veins. Okay, and these vessels called xylem and phloem they start out relatively far apart, but the higher they get, the more they taper together. Okay, so again, they start out far apart, and the further they get, they come closer and closer together. And what happens is it causes a water molecule to go up because of the surface tension of water. That's, by the way, why waters make nice, beautiful raindrops. Is surface tension. Surface tension. They're going to come together in nice droplets. Okay, so when it's raining out, you see water drop, come in droplet form and go down, on your windshield there. Okay, they come together. That's surface tension in action. Well, these droplets come together. Not only do they, slowly but surely make their way up the xylem and phloem of the tree, but as they notice, because of the taper effect, the adhesive forces of water start to stick to the edges of the xylem and phloem, and it's like an elevator going up. Okay, a very unique design system that God has employed. Okay, but it's called capillary action, the ability of water and the surface tension of water, the adhesive and cohesive properties of water to climb essentially a tube that tapers as it goes up. And the xylem and phloem of trees have that designed by God, not some silly evolution idea, not that would ever come about, but it's, you really see the design and brilliance of God as you study his creation, and that's one of them. That's how a tree gets water up to the very top. Okay, God is a mastermind. It's pretty awesome studying his creation. But that's capillary action, okay? So as we move on, I just want to spend a minute or two talking about evaporation and boiling. Okay, we're going to talk more about the phase changes that you're pretty familiar with already at a later time. But when we talk about evaporation and boiling, okay, the process whereby a liquid becomes a gas is called vaporization. So vaporization really is a liquid becoming a gas, okay? So liquid to gas. That's vaporization, okay? Now, believe it or not, water and liquids are always showing some vaporization. We call it evaporation. Okay, water is always evaporating. If I were to take a cup full of water, that's a terrible cup because it looks like a test tube. So let's do a cup full of water, okay? And we put the water line here. I'm sure you've experienced this. You get a glass of water before you go to bed, put it on a nightstand, and you leave it there for a few days because, you should clean your room and your mom's yelling at you to clean your room, whatever. But when you look, you'll notice that over time, this water level here is actually going to go down, okay? So all of a sudden, you're going to see, this thing go down, all right? I notice it goes down from its initial position. The reason why, okay, is that we said that water molecules, there's literally moles upon moles of water molecules in here, and they're not all moving at the same rate, okay? These things are moving around in this thing, some of them fast, some of them slow. Okay, that's, the slow one, then the fast one's like, they got different energies, and we talked about temperature being a measure of the average kinetic energy, right? But some of them are moving a little bit more quickly, and because some of them move a little more quickly, the fast ones, when they come to the top, they may just have enough energy to escape from the liquid all of a sudden into the gaseous state, okay? And that happens all the time. You get a fast one in here, all of a sudden it gets to the top and it's like, I'm out, I'm paroled, I'm out of here. Okay, but that's the picture that you essentially have, all right? Some of these molecules, water molecules in your cup, are moving faster than others, and it has nothing to do really of the temperature. I mean, obviously, the more temperature or heat or energy you add to the system, the quicker these molecules are going to go. But essentially, this is happening all the time. In fact, you see deposition, all right, or sublimation in your freezer. If you ever put water in the little ice creating bins there, and you just left it there for a long time, after a while you go back and you realize that all the water has evaporated out. This happens all the time. Evaporation is an ongoing process, okay? That's evaporation. Now, what's unique in boiling is a special type of phase change. And we'll talk more about this when we talk about the heating curve of water. But essentially, if I put a fire source under here, okay, and that's my fire, folks. Wow, that's pathetic. Okay, but that's my fire source. All right, I'm adding, obviously, heat to this system. Okay, so I'm just going to put it in as heat as kinetic energy. I'm adding kinetic energy to this system. All right, so these water molecules necessarily start moving around faster and faster. Okay, now what happens at boiling? You say, well, why does water boil at a certain temperature in New Jersey? The reason why boiling is a factor of two different forces. Okay, one of those forces, okay, coming down is something called the atmospheric pressure. Whether you recognize it or not, we'll call it, write that down, atmospheric pressure. Okay, I'm going to call it ATM for short. Okay, but ATM, write it in your notes, stands for atmospheric pressure. Okay, so there's a pressure exerted on us from the atmosphere. Now, God has uniquely designed us for our environment so we don't feel like always pressured. If your grandfather had leg surgery or hip surgery, a lot of times Grandpa will say, a storm must be rolling in, and you go, all right, Grandpa, but a lot of times he's right, because all of a sudden there's a high pressure system coming in. That's what a storm is. And all of a sudden the pressure, the atmospheric pressure gets stronger, and he can feel it putting more pressure on his hip. Or maybe your mom and dad are prone to migraines or something. The same thing happens when the weather starts to change. A pressure system comes in, a storm comes in, a greater pressure is exerted. And if you're sensitive because of a bad hip, bad knee, or just prone to migraines, you start to feel it. I remember this happens all the time. I remember being on a cruise a few years ago, and this guy was scuba diving. And if you've ever scuba dived, you're supposed to descend at a very low rate because the pressure is huge, right? The further you go down in the ocean, the greater the pressure. If you ever saw the movie The Abyss or something like that, you know this concept. Like, there's pressure the further you go. And what's interesting, we'll talk about this when we talk about gases in the next chapter, but what's interesting is the more pressure like a scuba diver feels. He's got his scuba on, he's breathing oxygen through that apparatus, the scuba apparatus, and the further he goes down because of the pressure, there's a law, I believe it's Henry's law, Hess's law, we'll get to it, but the higher the pressure, the more you can dissolve a gas. So the more you go down in the ocean, and as you breathe in that apparatus, you're actually able to dissolve more oxygen in your blood. Well, this guy on the cruise, he was going down pretty far, and he, by his own admission, I remember overhearing him telling that he walked into the dining hall and he could barely walk. He had like a cane, and he was like a big guy, and he was about to cry. I mean, he was in a lot of pain, and I was just caught my attention. He's explaining what happened to some of the other guests. So I was overhearing it. He said that he went scuba diving, and he was getting further and further down, nice and slow. You're supposed to descend slow, but at the same time, you're supposed to ascend slow as well. Well, he got down to a point, and he ran into a shark, and it freaked him out. So he just shot up. Wrong thing to do. The reason why is because when you get to a certain depth, there's more oxygen dissolved in your blood because of the pressure, and you're supposed to slowly come up, because when you slowly come up, it allows a slow time for that extra oxygen to come out. But if you shoot up, it causes all the oxygen to come up at once. It's a condition called bends, and it's extremely painful. So this guy was hobbling around. As I said, he wasn't no small guy either, and he was in pain. But going back to this idea of boiling, okay, again, there's an atmospheric pressure in New Jersey. There's an atmospheric pressure pressing down. Now, when I begin to boil things away, when I add heat to this system, what happens is there's an increasing pressure pushing up. That's called the vapor pressure. The more heat I add to the system, the more energy I'm adding to the water molecules, the further they're going, and there's a vapor pressure building. Okay? Boiling happens, okay, when the atmospheric pressure equals the vapor pressure. So in other words, when the pressure pushing down in the atmosphere is equal to the pressure pushing up from the vapor pressure, you're going to get boiling. And when we talk about this in a future class, you're going to see, very interestingly, that all the energy that goes into the system when a water is boiling, it's not raising its temperature any. All the energy is going to convert it from a liquid to a gas. But boiling happens when the atmospheric pressure equals the vapor pressure. That's why if you go really high, like up in the Alps, okay, you will essentially boil water at a significantly less degree, a few degrees less. So not 100 degrees, but like 97, 96 degrees, okay? So if you really want to get dinner in on time, all right, climb Mount Everest tonight. Your family will be happy. All right, don't know what that means. Anyway. All right, so moving on a little bit here. That's boiling. We'll review that a little bit more. I got to get rid of all this stuff before we can move on. So I feel like I'm rewinding here, freezing is is another phase change, okay? This is when, heat is being lost from the system. So if I input heat, I'm going to cause vaporization in the form of evaporation. Happens all the time. And then if enough heat is put in, the vapor pressure pushing up equals the atmospheric pressure pushing down, I'm going to get boiling. Freezing is the opposite, where you slowly take energy away, and it's this phase change from liquid to solid. Okay? So that's about all I really want you to know about liquids at this point. We're going to talk about more of the special properties, especially water and other liquids, when we talk about heating curves and phase diagrams. But for now, we're going to finish this presentation by quickly talking about solids. Solids are not really the subject of chemistry. Liquids are the subject of chemistry, and gases, really liquids. So we're not going to spend too much time here, but I do want you to know how to define solids in terms of the kinetic molecular theory. Okay, obviously in terms of kinetic molecular theory, solids is the state with the lowest energy in the molecules, between the molecules, and the highest forces of attraction. But do remember, and I stress this in class, even in the solid state, those molecules are moving. They are bound to each other, okay, but they're vibrating. Okay, even when we talked about bonding, I showed you I told you to think less of molecules as kind of bound on sticks between each other, and more as on springs. In fact, I showed you a few molecules with the springs. That's the best way to look at it. They're constantly moving. Okay, there's constant moving, and in class I told you the theoretical temperature at which all motion stops is called something called absolute zero, and it's based on the Kelvin scale of temperature, which technically absolute zero is negative 273 degrees Celsius. I mean, it's quite cold. All right, but for the most part, even solids outside of absolute zero, they are, even though they're fixed, they are always moving. But in this state of matter, obviously, you have the highest forces of attraction between the molecules and the lowest actual energy between them. Okay, so they're relatively fixed. And I want you to be aware of the fact that solids obviously take the definite shape and definite volume. Okay, liquids, remember, were definite volume, indefinite shape, and then gases were indefinite volume and indefinite shape. So they're contrasted in those ways. But solids, definite shape, definite volume. And the two things that I really want you to be aware of when it comes to solids is the difference between crystalline and amorphous solids, okay? An amorphous solid, amorphous, it's in the word, okay? Morph, okay, is that root means body. So when it says amorph, whenever you put a in front of a root, it means bodiless. So when you talk about amorphous solids, there's no real rhyme or reason. There's no body to it. It's like glass. Whereas crystalline solids, okay, this would be, by the way, an example of an amorphous solid here, okay? A crystalline solid, and we talked about this pretty much at length when we talked about ionic bonding. And here again, we have my favorite example in sodium chloride. For every sodium molecule surrounded by 6 negatively charged chlorine molecule, and every negatively charged chlorine molecule is surrounded by 6 positively charged sodium molecules. So you see a very structured repeating pattern called a crystal, okay, when it comes to crystalline solids. So I just want you really to be aware of the difference between the two solids. You can have amorphous solids, which are essentially bodiless, okay, don't have any repeating structure or pattern, and obviously that's to be contrasted with crystalline solids like ionic crystals, like sodium chloride pictured here, which are regular repeating patterns. Okay, so that's really all I want you to know on solids. You do have homework on this. Just the first 3 questions of chapter 10.3 review concerning solids, and then I think it's the other 6 for section 10.2 concerning liquids. Okay, all right. God bless you guys.